Hello everyone, we will continue inshallah. I will talk quickly about the inverse of a matrix, but the main topic that I want to talk to you about this lecture is how to get eigenvalues and eigenvectors. This is really very important for 2 by 2. As an introduction for the next lecture. The next one and the lectures of the next week is very, very important. So please try to attend them. Okay, now I want to get an inverse of a matrix. I can get the inverse of a matrix for a 2 by 2 or 3 by 3 using determinants. For a 2 by 2, there is a very quick way to get an inverse of a matrix. Let's say I have the matrix, which is 5, 3, 2, and 1. Ahmed, please turn the lights on. 5, 3, 2, and 1. I want to get the inverse of this matrix. This is matrix. It's very simple. If I have 2 by 2, the inverse is going to be very quick. All I have to do is to get the determinant of A, which is 5 times 1 minus 3 times 2, which is simply 5 times 1 is 5 minus 6, so it's going to come up to negative 1. It doesn't equal to 0, which means it's a non-singular matrix. So I can get its inverse. Okay. Now I will get the inverse. A minus 1 is going to equal to 1 divided by the value of the determinant times, look to this matrix. It is the adjoint matrix. أحمد شوف الadjoint matrix هجيبه ازاي؟ في حالة 2 by 2 بس. Replace the elements of the principal diagonal, which is going to be 1 and 5. And they change the sign of the secondary diagonal, which is negative 3 and negative 2. So all you have to do, replace the elements on the principal diagonal and then change the sign. And then divide on the value of the determinant, which is negative 1. So I will multiply each element of this element by 1 over negative 1. For 1, negative 3, negative 2, and 5. And so your inverse will be here, which is negative over 1, 3 positive, 2 positive, negative 5. That's the inverse of this matrix. The inverse of this matrix. How to know it is the correct inverse? Safe. If you multiply them together, the result will be a unit matrix. So to know that it is a unit matrix, it is correct, all I have to do is to multiply 5, 3, 2, 1 times the inverse, which is really very simple. Negative 1, 2, 3, and the negative 5. See this half? It's really very simple. Multiply the first row by the first column. 5 times negative 1, negative 5. Plus 3 times 2, 6. The result is 1. Try to multiply the first row by the second column. So it's going to be 5 times 3, 15. Plus 3 times negative 5, negative 15. So the result will be multiplying the second row by the second column, by the first column. 2 times negative 1, negative 2. Plus 1 times 2, the result will be 0. Multiply the second row by the second column. 2 times 3, 6. Minus 5, the result is 1. So the inverse is really, very quick. All you have to do once more, evaluate the value of the determinant, then replace the elements of the principal diagonal and the sides of the secondary diagonal. Then divide on the value of the determinant. You are done. If I want to evaluate for a 3 by 3, the process will be a little bit different. I will get the cofactor method. Okay, it's really very important with all what we are taking. It's another method to get an inverse for a 3 by 3 matrix you should know about. So if I have my matrix is given by, please turn the lights off just for a second. I will get the numbers, which are 3, 0, and 4. And then I will have 2, 1, and 0. Then the last row is going to be negative 1, 0, and 1. Then the lights on once more. Okay, I will need to evaluate the value of the inverse. How to get it? First of all, get the value of the determinant. So very quickly, the choice is yours. Are you going to use Sarah's rule or the other method? Okay, first use SAS because this is the fastest method. This is A. Okay, with me. 3 times 1 times 1, 3. Then plus 0 times 0 times negative 1 is done. 0 times 2 times 4 is done. Then minus 4 times 1 times negative 1. It's a minus of a negative 4. Minus 0 times 0 times 3, 0. 0 times 2 times 1, done. So the result will be 7. And it's not equal to 0. So it is a non-singular matrix. So I can get the inverse. The second step is very important. The step that we are going to do right now. Remark, I will write the elements, ya hazim, which are A11, A12, A13, equal to, equal to, equal to. Then A21, A22, A23, and then the element A31, A32, A33 equal to, equal to, equal to. Those are, if you look to those elements, look in depth, Mr. Safe. These are the elements of the first row, but it is written as a column. So actually, I made 2 steps in 1 step. I'm getting the cofactor, and then I will do the transpose. So once more, look to the values. It is the values of the second row, but it's written in a column. And that's the values of the third row, but also written as a column. I will go for each one of these elements, eliminating the row and the column, respecting the sign rule. Can you write the sign rule for me? Positive, because the sum of these 2 numbers is even, am I right? So it's going to be positive, negative, I will put the sign. Positive, negative, positive, then negative, positive, negative, positive, negative. Am I right? In front of each element, eliminate the row and column and evaluate the determinant. So I will go for 1 and 1. This is the first row, first column. Get the value of this determinant. I will write it for the first one only. 1, 0, 0, 1. So the value is going to be positive 1. Do it with me, Ahmed, with the element 1 and 2. This is first row, second column. So I will eliminate the row and column. 2 times 1, 2, minus 0. So it's going to be negative 2. I will go for 1 and 3. This is 1 and 3. Eliminate the row and column. 2 times 0, 0. Minus negative 1, which is going to be positive 1. Please be careful about the sign conversions. I'm going for the element 2 and 1. Hala, that's the second row, first column. That's the element. Eliminate the row and column. It's going to be 0, 4, 0, 1. You don't have to evaluate. The value is equal to 0 because you have a complete row or a complete column is equal to 0. I will go safe for 2 by 2. That's the element 2 by 2. Eliminate the row and column. Eliminate the row and column. Evaluate. 3 times 1, 3. Minus negative 4, which is going to be positive 4. 3 plus 4 is equal to 7. I will go for 2, 3. This is second row, third column. It's going to be 3, 0, 0, negative 1. So you don't have to evaluate the value. The value is going to be 0. Do it with me once more, ya. Okay? I'm going for third row, first column. Third row, first column. So it's going to be 0 times 0, 0. Minus 4. So the value is going to be negative 4. Go for 3 by 2. Eliminating row and column. 3 times 0, 0. Then minus 4 times 2, which is going to be a negative 8. So third row, second column. Okay? 3 times 0, 0. Minus 8. Of course, the sign is negative, so it's going to be positive 8. I will go for the last one. Eliminating row and column. 3 times 1 is equal to 3 minus 0. So the number is 3. These are the values of the cofactors. I will put them all in one matrix, which is called the adjoint matrix. So the inverse simply is going to be 1 over the value of the determinant times the A adjoint matrix. So simply it's going to be Write the values of all of these numbers, which are 1, negative 2 and 1, then 0, 7 and 0, then negative 4, 8 and 3, then divide each one of them, of these numbers, on the value of the determinant, which is 7. So all of them will be divided by 7, as you can see, and from here you can get the inverse really very quickly for each of these numbers. That's the inverse. Turn on the light. The matrix or the determinant or this method is called the cofactor method. For a 2 by 2 once more, 5 times 1, 5, minus 6 is going to be negative 1. I can get the inverse very simple. 1, 5, negative 3, negative 2 divided by negative 1. So all you have to do is to get the inverse. Here is the inverse of the matrix, exactly as we checked previously. For the 3 by 3, I will go with the same results as I told you. The value of the determinant is 7, isn't equal to 0, which means it's a non-singular, so you can get the inverse. I will start getting the cofactors, that's the sign rule you have to memorize. These are the elements B11, B12, B13. As you can see, 1, negative 2, and 1. Exactly like 1, negative 2, and 1. That's the elements of the second, and that's the elements of the third column. I will put them all together in the adjoint matrix. That's the adjoint matrix. Here we go. That's the adjoint matrix. I will divide each number of these numbers on 7, and that's my inverse in front of you. This method is very quick and very successful if you have 2 by 2 or 3 by 3. I usually, between using Gauss elimination, the method that you used, the method that you used for inverse previously, and also this method. So I'm between both of them. Of course, I already gave you previously how to evaluate an inverse for a 2 by 2 matrix, because we needed in Mintoff application, if you remember. We get A minus lambda, A minus I, then we get the inverse similar. Now I'm going to talk about a very important topic, and this is the eigenvalues and the eigenvector. In this lecture, I will do one problem. And this problem will be sequences, step by step. It's a systematic method to get the eigenvalues for a 2 by 2. If I'm dealing with 3 by 3, the process will be a little bit harsh than this. And we will go through it next week. Okay? Inshallah. Okay. My way, getting the inverse for a 2 by 2 matrix. I will cut all of this because you already have them. Okay, I will go to the main steps. I want to review the main steps with you, step by step. The reason I'm getting the eigenvalue and the eigenvector for this matrix. Please try to follow up with me as much as possible. This is really very important problem. We will go through it together. Just in a second. The matrix A, which is 9, 2, 2, and 6. That's the matrix that I want to get its inverse. Okay, in the right. Okay, I want you to focus as much as possible. I will need just a second. I don't think we, okay, just let's do like this for the timing. Okay. Okay, I need to get the eigenvalues and the eigenvectors very quickly. So what to do? The first step, I will have to solve this equation, which is A minus lambda I in a determinant equal to 0. This is step number 1, which is called the characteristic equation, or the equation where I will get the eigenvalues. Look at it carefully. It's an A minus some constant, which is lambda, this is what we call eigenvalues, times I, which is a unit matrix from the same dimension as I. That's, I'm going to have a determinant for 9 minus lambda 2, 6 minus lambda equal to 0. That's the result. Once you make the subtraction between this matrix and the unit matrix here safe is minus 1001. And it is times lambda. So all the elements that will be affected are the elements of the principal diagonal. Are you with me? Okay, now I'm going to expand, expand this matrix. I'm sorry, this determinant. How to expand? I will multiply the elements of the principal diagonal minus the elements of the secondary diagonal. So simply it's going to be 9 minus lambda times 6 minus lambda. Then minus 4, which is going to equal to 0. Are you with me? Multiplying the elements of the principal diagonal minus the elements of the secondary diagonal. Now, try to expand this equation, which is going to be 9 times 6, which is going to be 54. Then 9 minus lambda, minus 9 lambda, 6 minus lambda, so it's going to be negative 6 over lambda. Negative lambda times negative lambda is going to be lambda squared. Then I have my negative 4 equal to 0. Gathering and rearranging, you will have lambda squared minus 15 over lambda plus a 50, and it's equal to 0. Can you see it? This is what's called the characteristic equation. I can solve this quadratic equation very, very simple. Either by factorizing or by using the law. It's a quadratic equation, which is very, very simple. It's going to lead to having these two brackets equal to 0. Lambda, 5, 10, negative, negative. So I can say lambda 1 is equal to 10 and the lambda 2 is equal to 5. Those what's called eigen values, and this is important. Relative to each value of these values, I can get what's called an eigenvector. How to get an eigenvector? All I have to do is to solve a homogeneous system, which is the system that I'm going to use. So that's the first part, getting eigenvalues. Now I'm going to move to the second part, which is getting eigenvectors. I understand, say? So this is mainly step 1. I'm going to step 2. To each one of these values, I will have a vector. The vectors will come from solving a system, which is A minus lambda I times x equals 0, which is an homogeneous equation. I will get the first vector. I will do like this. Just in a second. Okay. So I will solve when lambda is equal to the first value, which is 10. Okay? Let's sub together. Let's make a substitution in the system, replacing every value of lambda by 10. So this half, simply, it's going to be 9 minus 10. So it's a 9 minus 10. Then I will have 2. The result is 0. For the second row, it's going to be 2. Then 6 minus 10. 6 minus 10. And the result will be 0 also. Are you with me? Okay. This will lead to, this system is going to be 9 minus 10 is going to be negative 1. 2. Then 2. And the 6 minus 10 is going to be negative 4. If you look closely to this system, you will discover that you have a system that will lead to infinite number of solutions. Because simply the first row is going to be 1, negative 2, and 0. I'm trying to reach an echelon form. So I will multiply the first row by negative 2 and the add on the second row. Ahmed, negative 2 plus 2, the result will be negative 2 times negative 2, positive 4, plus negative 4, the result will be, and then the final is going to be 0. خلي بالك مستر حازم، This is U1, vector 1, first component. That's vector 1, second component. Expand it as an equations, which means the first component of the first vector is equal to 2 of U1, 2. Are you with me, Hala? I multiply 1 times U1, 1, then negative 2 times U1, 2 equal to 0. Then I've moved it to the other side. So it is leading to U1, 1 is equal to U1, 2. Now I will be able to get the value of the vector. It's an infinite number of solutions. So once more, this is U1, which is U1 sub 1, U1 sub 2. Please do make the replacement. So it's gonna be 2U1, 2, U1, 2. Both U1, 2 equal to 1. This is gonna be 2 and 1. Of course, putting U1, 2 equal to 1, this variable, you can put it 1, 2, 3, any number. But in this case, the simplest to have integers is to use 1. Hala, I will do exactly the same, once more. But with the value of lambda equal to 5. Please do it. Okay, that's the matrix. That's the determinant. Replace lambda by 5. Let's do it together. 9 minus 5, it's 4. Then I will have 2. For the second row, this is going to be 2. 6 minus 5 is going to be 1. Are you with me? And those are zeros. Am I right? Okay, once more. Try to put this matrix on an echelon form or reduced echelon form. So I will need this number to be positive 1. How to force 4 to be positive 1? I will divide the first row on 4. Okay, so the new matrix will be like this. That's the new matrix. 4 divided by 4 is going to be 1. 2 divided by 4 is going to be 1 over 2. Then the result is 0. ماشي؟ عشان اقدر اجيب الفيكتور التاني. هو ده فيكتور. Relative للقيمة اللي هي بتاعتها. I'm doing the same exact steps but with number equal to 5. مش هتفرق معايا. Continue. لا مش هسأل. Continue. I will multiply negative 2 and add. اشتغل كده معايا. Negative 2 plus 2. Negative 2 times half negative 1 plus 1. The result will be. Okay. Of course, you will have a complete row equal to 0 because you are using the eigenvalues. So actually, you are obligated this problem to have a complete row of zeros. Are you with me? Now I have the condition. What's the condition? That's or the relation. This is the second vector, first component. Second vector, second component. Please expand it as an equation. How? معايا. 1 times u2 1 half times u2 2 plus 1 over 2 u2 sub 2 equal to 0. Now get one of them as a relation of the other. معايا. يبقى u2 1 is equal to negative half u2 sub 2. Now I can do the vector. Use the vector. u2 is equal to u2 first component, u2 second component. Now use the replacement. I will replace u21 by negative half u22, and this is u2 sub 2. Now the both components are with respect to u2 sub 2. Am I right? Choose any number. It's an infinite number of solutions. No, I will use 2. عشان half. You are free to use any number that you like. I will consider u2 sub 2 is equal to 2. Why? To get rid of the half. So the result will be negative 1 and 2. This is the result. Okay, look to these two look to these two vectors. That's the first vector, and that's the second vector. These two vectors, these two vectors are very, very important. Why they are very important? Because each eigenvalue corresponds to an eigenvector. From both of them, I can get what's called a model matrix. This is what's called a model matrix, where in this eigen space, the first eigenvector will be the first column, which is going to be 2 and 1. And the second column is going to be the second eigenvector, which is going to be negative 1 and 2. This matrix is very important. This matrix will help you out in order to put a diagonalization for the main matrix that you will deal with this matrix. So this is the model matrix. Those are the numbers, as you can see. Actually, in most of the applications, we use a unit vector, not just only any vector. How to change any vector to be a unit vector? I will have to divide the elements of the vector on its magnitude. What's the magnitude? The sum of the squares of the components. Remember, here I will choose the u12 to be equal to 1. Here I will choose the u22 equal to 2. You can use any other number. I need to make it as normalize our work. So I will divide each column by the sum of the squares of these elements. So square 2, which is going to be 4, plus 1, which is going to be 5. I will divide each number on the square root of the sum of the squares of these values. This is the best method to find it. Here too, it's exactly the same. This matrix, we will call it B. And this matrix has a very unique property, that its inverse, okay, is the transpose of this matrix. It's an orthogonal matrix. So this matrix, once you are dealing with a symmetric matrix at the beginning, it's a transpose in the inverse. So remark, if I multiplied this matrix, which is B minus 1, the transpose, times the A matrix, given matrix, times B, I will get a diagonal matrix. This is a diagonal matrix. And the elements of this diagonal matrix are the elements of the eigenvalues, which are 10 and 5. So, once more, if you get the inverse of this matrix, which is the transpose, so it's going to be 2 over root 5, 1 over root 5, minus 1 over root 5, 2 over root 5, that's the inverse. And if I multiply it by 9, 2, 2 and 6, then multiply by this matrix once more, 2 over root 5, negative 1 over root 5, 1 over root 5, 2 over root 5, the result will be a diagonal matrix with the eigenvalues on the diagonal. This lengthy process is called diagonalization. It's called diagonalization. And diagonalizing this matrix, it will make your life a lot easier in dealing with this matrix down the road. Imagine, instead of dealing with a matrix, you are dealing with a diagonal matrix, and you know the relation connecting them together. It's going to be very simple. So once more, this is called diagonalization. Okay? I will repeat all the steps once more for this problem, and they will end our lecture now. After evaluating all of this. Okay? Turn the lights off, please. Okay. Once more. This is our matrix. Hey. This is our matrix. The first step, I will get the eigenvalues. So all I have to do is to evaluate the determinant. I will get the principal diagonal minus lambda, and I get the value of the determinant. Here we go. 9 minus eta, whatever, 2, 2, 6 minus eta. I will expand it, which means I will multiply the elements of the principal diagonal minus the elements of the secondary diagonal. That's the equation that I'm going to solve. I'm going to simplify it and end up of having lambda 1 negative 5, lambda 2 minus 10. So lambda 1 I will consider in this solution 5 and lambda 2 is equal to 10. Replacing them will cause nothing. It will replace the terms, okay? So this is 5 and that's 10. The second step, I will get the eigenvectors. How to get the eigenvectors once more? This is u1, which is relative to lambda equal to 5. So I will go right in the system, 9 minus 5, 2, 2, 6 minus 5. That's the system that we are talking about, which is simply 4, 2, 2 and 1. I will multiply the first element or divide the first row by 4, which is going to be 1.5. Then multiplying in negative 2 and adding to the last row, I have my relation that the first u1 sub 1 is equal to minus 0.5 u12. That's the relation that I'm telling you about. This is u1 equal to negative half u12. I will consider u12 is equal to 2 to get rid, in order to get rid of the 0.5. So those are the relation. Replacing u21 by 2, that's the vector u1 and 2. I will repeat the same exact steps, but in this time, using lambda 2 is equal to 10. So I will make the substitution 9 minus eta 2, 2, 2, 6 minus eta 2, which is going to be simply 9 minus 10, 2, 2, 6 minus 10. Continuing the steps is going to be negative 1, 2 and 0, 2, 9 minus 4 and 2. I will multiply negative 1, then multiply 2 and add. Now I have my relation connecting the second components of the second vector, both together, which is exactly the same. So u21 is equal to 2u22. I will use, instead of u22, 1 in order to get my vector, so the vector is going to be 2 and 1. Now I have the two vectors. I can now get simply the model matrix that I'm telling you about. Negative 1, 2, 2 and 1. I will divide each component on the square, on the sum of the squares of the components. So simply 1 plus 4 is going to be 5, divided by root 5, divided by root 5, and so on. That's u. U minus 1 is the transpose of this function, multiplies the third step. First of all, those are inverses from each other. If you multiply u to make this to prove that it's equal to unit matrix. Diagonalization. That's the matrix, that's matrix A, that's B. And if you multiply them together, the result will be 5 and the 10, 0 and 0, which are the value of the eigenvalues. Are you with me? I will continue next time. You have plenty of problems on a 2 by 2 with exactly the same result in order to make you actually being capable of doing this on your own. Thank you very much. And I'm sorry for the long lecture of today. I will continue next time, inshallah. Thank you very much. Thank you. Bye.